Today we're going to learn about some more concurrent lines for triangles, and they are medians and altitudes. So first let's find out what each one of those things is, and as always don't forget your summary and essential question at the end of the lesson. A segment whose endpoints are a vertex of the triangle and the midpoint of the opposite side is a median. A median of the triangle. And of course, if I have three of those, they're going to have a point of concurrency. The point of concurrency of the medians of a triangle is called the centroid of the triangle. So let's just look. I'll just draw an acute triangle here. All right, so the endpoints are a vertex of the triangle and a midpoint of the opposite side. So looking for the midpoint of every side, midpoint of every side. All right, and then to get the median, I got to go from each midpoint to the opposite vertex. So there's a median, here's this median, and here's this median from the vertex to the midpoint of the opposite side. So all three of those are medians, and of course where they meet, their point of concurrency, that's the centroid. And as you would expect, we have a theorem about the concurrency of the medians. The medians of a triangle intersect at a point that is 2/3 of the distance from each vertex to the midpoint of the opposite side. So I'll come back down here to this example in a minute, but let me take the one that I drew here. So let's see what this means here. Let's look at my green median here. Okay, everybody look at my green median here. And let's just say that that is 24 inches long. Okay, let's say the green median, and they won't all be the same. They would be in what kind of triangle? An equilateral triangle, right? But assuming this isn't an equilateral triangle, then all the medians will be different lengths, but I got this one here. I'm going to tell you, I'm just saying given it's 24 inches. So what this theorem tells me is that this part right here from the vertex to here to the centroid is 2/3 of the total length. So let's call that D. So I know that D is 2/3 of 24. Which is going to be 16. So 16 inches. So D, so from here to here is 16 inches, which means from the centroid to the midpoint of the opposite side would be the other 1/3. So this little part right here would be 8 inches. Okay, that's all that theorem is telling you. So let's go to the example that's already written here. If P is the centroid of ABC, P is the centroid of ABC, I know that AP, so here's AP, I know that it's 2/3 of the whole thing, which is AD. I know that BP is 2/3 of the whole median, which is BF, and of course CP would be 2/3 of CE. And just like the end center, for every triangle, any and every, the centroid is always inside. Not only is it always inside, but the centroid is also known as the balancing point. Balancing point of a triangle. So theoretically, if you had a solid triangle, you know, made of wood or maybe even cardboard or something, if you located its centroid, then you could place maybe your pencil point on that centroid, and you could balance that triangle there. Hey, why don't you give it a try? Centroid is the balancing point of the triangle. Okay, well, let's move on from the centroid now, exciting as it may be, and talk about the perpendicular segment from a vertex. So let's take us another triangle here. Perpendicular segment from a vertex to the opposite side or to the line that contains the opposite side. Okay, we'll get to that, the line that contains the opposite side. Let's look at this. Let's take this vertex right here, and I want a perpendicular segment. So I need a line that starts at this vertex and is perpendicular to the opposite side. So that would be that one right there. So there is, and that's called an altitude. Guys, that's an altitude. We already knew that. Oops, spelled it wrong. Altitude. So from a vertex to the opposite side, perpendicular, doesn't go to the midpoint of the other side. That's a median. Okay, perpendicular to the opposite side is an altitude. So let me try to find this one. Let's see. That one looks like it'd be about like that. And then this one here looks like it would be about like that. And you see, of course, they also have a point of concurrency. All those altitudes have a point of concurrency, and that point of concurrency is called the orthocenter. Orthocenter of the triangle. So now we've got 4 points of concurrency that you've got to know how to keep straight. Circumcenter, incenter, centroid, orthocenter. It's a lot. You got to be doing those flashcards. And of course, we have a concurrency of altitudes theorem that says the lines containing the altitudes of a triangle are concurrent if HE, BD, and CF are the altitudes of triangle. Oh, I guess that was the end of it. That was the end of it. I couldn't see my period there. The lines containing the altitudes of a triangle are concurrent, just like the lines containing the perpendicular bisectors and the angle bisectors and the medians. All right, so here we go. If HE, BD, and CF, so here they are, HE, BD, and CF are the altitudes of ABC, then the lines HE, BD, and CF intersect at some point we're calling A here. So while the altitudes are a segment, may be a segment, this theorem is just telling you that the lines that contain those segments, those altitudes, are concurrent, will always be concurrent. However, unlike the centroid and the incenter, the altitudes the orthocenter may occur inside, outside, or on the triangle, just like what other one? The circumcenter. So if we have an acute triangle, the orthocenter will always be inside. If we have a right triangle, the orthocenter will always be on. And if we have an obtuse triangle, the orthocenter is going to be outside. Outside the triangle. And this is one that's, I would say, more difficult. Let me look here. I don't have an example, but what's going to happen? Let me just come aside and show you here. If I have an obtuse triangle, okay, pay close attention to this. Okay, if I want to find the altitude from this vertex to the opposite side, no problem. It's right there. There's the altitude. Okay, let's find the altitude from that vertex to the opposite side. Look, I can't find it. I cannot find it. I can't drop a perpendicular from the red vertex to this side right here. So what do I have to do? I actually have to extend this side of the triangle, and then I can drop the perpendicular. So there's the altitude that goes from this vertex to the line that contains this side of the triangle. So when you have an obtuse triangle, you have to extend two of your sides. So now let's look at this. This is the vertex we haven't chosen yet. So also, I cannot draw a perpendicular segment from this vertex going through the inside of the triangle. So once again, I have to extend my triangle side until I can drop a perpendicular. Okay, so there's my altitude, the perpendicular segment to the line that contains this side of the triangle. Okay, and now what do I have to do to find their point of concurrency? Well, I have to extend all these until they finally meet up. I had to curve that one a little because I freehanded it. But so that's how your orthocenter ends up outside the triangle when it's an obtuse triangle. We'll do a lot of practicing on this in class because it is a bit complicated. All right, so now we're just going to do some examples. R is the centroid. What is the centroid? It's the point of concurrency of the medians. So I'm going to write myself a note here. Remember how I told you I like to do that? R is the centroid, point of concurrency of the medians, and SR here, SR is 16. Find SV. So I got to find the length of that entire median. So what do I know? I know that SR is 2/3 of SV, right? That's what the theorem told me. The distance from the centroid to the vertex is 2/3 of the total distance from the vertex to the midpoint of the other side. So what do I know? I know that SR is 16, so that's 2/3 of SV. Now how do I get rid of that fraction over there? I multiply both sides by its reciprocal. So multiply both sides by 3/2. That's going to get rid of my fraction here, and what I end up with is, let's see, 2 goes into that 8, so 24 equals SV. All right, that's how you're going to work that problem. What does RV equal? Well, of course, it equals 8. 16 plus 8 has to be 24. All right, what do we got here? Ooh, a little coordinate geometry. Find the coordinates of the centroid of DEF. Okay, well this is nice because I got this horizontal line here. So the centroid, so what do I know? Well, I have one median drawn here, right? I have this median drawn here. So basically all I got to do is find its length, right? I got to find its length, and then I got to take 2/3 of it. Okay, so what's the length of EJ? Well, if it was any other kind of triangle where this side wasn't horizontal, I'd have to use the distance formula, wouldn't I? I'd have to find the distance formula to find out how long EJ is, but I don't have to do that in this case, so I'm not going to. All right, so how long is it? Well, it goes from 7 down to 1, so EJ is 6 units long. So the centroid is going to be 2/3, located 2/3 of that distance. So 2/3 of 6 equals 4. So if I just start from this vertex and count down 4, 1, 2, 3, 4, there's my centroid. I'm going to call it C. And what do I need? I need the coordinates. What are the coordinates there? The coordinates are 5, 3. So that was an easy one because I had that horizontal line. If the median had not been a vertical line so that I could count, I would have had to use the distance formula to find out how long it is. All right, here we go. Triangle ABC has vertices. All right, when I get a problem like this, I want to get myself a fairly accurate sketch. I'm not going to draw the grid, but I am going to try to make something fairly accurate. So I've got point 1, 3. So that'd be about right there, point A. And then B is about 2, 7. So we'll put that right there. And C is about 6, 3. Ah, another horizontal line. Thank goodness. So here's A. This is C. C and B. Draw my triangle here. What are the coordinates of the orthocenter? Okay, I'm looking. Orthocenter is the point of concurrency of the altitudes. So I could pick any altitude, but the logical, well, actually I got to find, what have I got to do? I'm going to draw these. I'm going to draw all my altitudes. So here's going to be this one. Okay. From A to BC, that looks perpendicular to me. I'm eyeballing this, and that's what you need to do too. And then from C, that looks like it. So that looks like my orthocenter right there. So how am I going to find the coordinates? You know what I got to do? I got to find the equation. This kind of goes back to like we did with mid-segments. I got to find the equation of two of these altitudes, and I got to set them equal to each other. So why don't we do the easy thing, and I'm going to put my numbers up here. So A is 1, 3, C is 6, 3, and B is 2, 7. So let's call this, I need some letters here. So let's call ABC, let's call this D, E, F. All right, we need letters there. So I know the equation for BF. The line BF, if the X value is 1, then the equation for BF, oh, I'm sorry, it's 2. B is at 2. Look, B is at 2, 7. So the equation, got to be careful here. We may have to redo this one in class. But you see this line right here that contains BF, it goes through this point X equals 2. So BF's equation is X equals 2. So that's an easy one. So now all I got to do is find an equation of one of the other ones. So I don't know. Why don't we pick AE? Let's look at AE. Try to find its equation. How am I going to do that? Well, I know I got a point. I need the slope, right? I need the slope of AE. How can I find the slope of AE? Think about it. Think about it for a second. Oh, I know the slope. I can find the slope of BC. So let's find the slope of BC. Slope of BC, it equals 3 minus 7 over 6 minus 2, which is negative 4 over positive 4, which is negative 1, right? But how does that help me with the slope of AE? Oh, because it's perpendicular, so it's the negative reciprocal. So the slope of AE is going to be positive 1. Okay, so now I've got the slope, I got a point on the line, so I'm going to use my point slope form, and I'm going to say y minus 3 equals 1 times x minus 1. So I got y equals x minus 1 plus 3. So y equals x plus 2. Right, so that's the equation of AE. This is line AE right here. Okay, so I've got BF, I've got AE. So now to find their point of intersection, I'm going to set them equal to each other. Well, I know that x equals 2, right? X equals 2 from right here. So I'm just going to plug that right into here. So y is going to be 2 plus 2, which is 4. So if x is 2 and y is 4, that means my orthocenter, which we'll call O, is at 2, 4. All right, that's it. Oh, I think there's one more. Let's see. What are the coordinates? You know what? This is pretty similar to the one I just did. And since we're already running long here, over 20 minutes, I'm going to save this as a practice for you. And I will put the solution up here and you can check your answer and we'll talk about it in class if you need to. I've put the solution here for this problem for you, so I really want you to work through it. Remember, anytime you're trying to find the orthocenter, you need to find two of your altitudes, equations for two of your altitudes. So first, sketch the triangle. Second, sketch in two of the altitudes. Find the equations for both of those altitudes, the equation of the lines that contain the altitudes. All right, set them equal. However, if one of your equations is just x equals something or y equals something, you really just need to find the other equation and then plug that in, which is what we did in the previous example and here. And what we found here, which is fantastic to know, is that whenever I find the orthocenter of a right triangle, remember how I told you it would always be on the triangle? Well, not only will it always be on the triangle, it will always be at the vertex of the right angle. So that's the wonderful discovery that we have made here with this problem. Please go back and work through it. If you didn't, look through these and let me know what questions you have when I see you next in class.